Welcome to BTEC Revision. In today's lesson, we're looking at transformers. By the end, we should be able to describe how transformers work and calculate the voltages, current, or number of coils in transformers. First, we need to look at what mutual inductance is. Mutual inductance is a property of two coils in close proximity to each other, where a change in current in one coil induces an electromotive force in the other. For example, mutual inductance is used in transformers. Now let's look at a transformer. What is a transformer? It is a electric. Now we can look at transformers. What is a transformer? A transformer is an electrical device that is used to transfer electrical energy between two or more circuits through electromagnetic induction. Transformers are widely employed in electrical systems for the transmission of electrical power as well as in electronic devices. Here we have a picture of a transformer. We can start by looking at what the primary and secondary coils do. Looking at the left side of this transformer, we have the primary coil on the left and the secondary coil on the right. The primary coil is connected to the input voltage and the secondary coil is connected to the output load. The coils are wound around the same magnetic core, which facilitates the transfer of energy between them. As you can see here on the left, we have the voltage in the primary coil, and on the right side, we have the voltage in the secondary coil. And the left side, we have the number of primary coils, and on the right side, we have the number of secondary coils. Next, we can look at how magnetic flux plays a role in transformers. Magnetic flux is generated by varying the current in the primary coil. The current needs to be AC. The flux flows around the core and induces an EMF in both the primary and the secondary coils. And if you remember, induces means to generate. The core is made from ferromagnetic material, such as soft iron, or we could also use laminated steel to minimize losses caused by eddy currents. And here is the soft core, which is a ferromagnetic material, i.e. iron. And here is where the magnetic flux is flowing. When an alternating current flows through the primary coil, it produces a changing magnetic field around the coil. This changing magnetic field induces a voltage in the secondary coil. We have two types of transformers, a step-up and a step-down transformer. Transformers can step up or step down the voltage between the primary and secondary coils. A step-up transformer is going to increase the voltage, while a step-down transformer is going to decrease the voltage. And this is very important in order to transmit electrical power over long distances. How do we calculate the voltages and number of coils in transformers? We have this equation, which is stating that the primary voltage divided by the secondary voltage is equal to the primary number of coils divided by the secondary number of coils. So this is the ratio of the voltages is equal to the ratio of the number of coils. And the short form is V1 divided by V2 equals N1 divided by N2. And looking at the units, number of coils does not have any unit, so N1 divided by N2 has no unit. And voltage has unit of volts, so volts divided by volts is just 1, therefore this side has no units either. In a step-up transformer, the voltage ratio V1 divided by V2 is going to be less than 1. In a step-down transformer, the opposite is true. The voltage ratio V1 divided by V2 is going to be bigger than 1. Now, let's take a look at an example. If a transformer has a primary voltage of 240 volts, a secondary voltage of 120 volts, and 200 primary coils, calculate the number of secondary coils. We can start by writing down our equation. V1 divided by V2 equals N1 divided by N2. And we could rearrange for N2, or we could put in the numbers first. Either way is fine. So I'm going to rearrange the equation first. So I'll times both sides by N2 to give me N2 V1 divided by V2 equals N1. And now I can times both sides by V2, and that will give me N2 V1 equals N1 V2. And finally, divide both sides by V1. So that's N2 equals N1 V2 divided by V1. And we can plug in our values. N1 is the number of coils in the primary, which is 200, times V2, so the secondary voltage, that's 120, divided by primary voltage, which is 240. And that's going to give you a value of 100 turns. Next, we can take a look at how voltage and current are related. Considering no energy is lost in a transformer, then the following equation applies. The primary voltage divided by the secondary voltage is equal to the secondary current divided by the primary current. Note that we have secondary first in the right side of the equation and primary comes second. The short form is V1 over V2 equals I2 over I1. Let's look at this example. A transformer has a primary voltage of 240 volts, primary current of 6 amps, and a secondary voltage of 2 volts. Calculate the secondary current. We start by writing down our equation. V1 over V2 equals I2. This time it's I2 over I1. Okay, so try not to get this confused with the previous equation, which is V1 over V2 equals N1 over N2. So we can rearrange this for secondary current. Okay, so for this one, we just times both sides by I1. So secondary current equals primary current times voltage in the primary divided by secondary voltage here. And now we can plug in our values. So the current, primary current is 6 times the voltage in the primary, which is 240, divided by the voltage in the secondary coil, which is 2. Therefore, that would be 360 amps. Therefore, that would be equal to 720 amps. Now pause the video here and attempt this exam question. A transformer has 100 turns, a voltage of 100 volts, and a current of 5 amps in the primary coil. The secondary coil has 1000 turns. If the transformer is 95% efficient, calculate the current in the secondary coil. We can start by writing down what we have. So in the primary coil, we have N1, which is 100 turns, V1, which is 100 volts, and current, I1 equals 5 amps. In the secondary coil, we have N2, which is 1000. We don't have V2, that's the question, and same for I2. We also have efficiency, which is 95%, and we're going to write that as decimal, 0.95, to make our calculations much easier. Now we can start by working out V2, and we know the equation for this. V1 over V2 equals N1 over N2. Now to rearrange for V2, I'm going to inverse both sides. So that's V2 over V1 equals N2 over N1, and then times both sides by V, and that will give me V2 equals V1 times N1 over N2. Therefore, plugging in our values, so V1 is 100, and N1 is also 100, divided by N2, which is 1000. And this gives me a value of 10 volts. So V2 is 10 volts. Next, we can work out the current in the secondary coil. So in order to do that, what we could do is work out power because we have efficiency. Okay, 0.95. We know the efficiency is equal to the power out divided by the power in. So in our case here, power out is going to be in the secondary coil. So that's P2. And then power in is what's coming in from the primary coil, so that's P1. So if you rearrange for P2, that's equal to the efficiency times P1. So that is 0.95 times P1. Now remember power, the equation power is current times voltage. So we can times these two values. Okay, so we write over here, P1 equals I1 times V1. So that is 5 times 100. So that's 500 watts. So we can put that in this equation. So that's times 500. And that gives us a value of 475 watts. Now, if you remember our other equation for power, which is IV, so for P2, that would be P2 equals I2 times V2. You can rearrange for I2, which is P2 over V2. We worked out P2, so that is 475. And we have also worked out V2, which is 10. Therefore, dividing this, that will give us our value of 47.5 amps. And that's the end of the lesson. If you'd like to boost your grades, visit us at btechrevision.com. See you.